It's a great pleasure to have Masashi as a JAC speaker for today. So just a few words to introduce Masashi. He's a professor of physics at KEC, Japan. He started his academic career in experimental physics, particle physics, and then changed his focus to observational cosmology, in particular for CMB polarization. So in terms of particle physics, he was involved in the Bell experiment and the discovery of CP violation in P meson decays. And then in cosmology, he has been the founder of the LiteBIRD project. And also he has worked in PolarBIRD, discovering the first, participating in the discovery of the first CMB polarization lensing measure. So he was also the founding director of Quantum Field Measurement Institute at KEC, and he proposed novel measurement with quantum sensor. So he received the JSPS prize, and also he was appointed as a member in the Nicholas Copernicus Academy in Poland. So Masashi will talk about fundamental mysteries of nature and CMB polarization.
Thanks, Fabio. Since my views are probably a bit different from yours, let me first give you some self-introduction, well, which was already explained, but I started my career as a particle physicist, experimental particle physics, and I worked on the B factory at KK, and then turned to experimental cosmology, namely for CMB, B-mode polarization measurements. I started from Quiet project, and then Polar Bear Simon's array, and then proposed LiteBIRD. Technology-wise, I started my career with the development of the semiconductor detectors, and then turned to the superconducting detectors for B-mode observations. And then recently, I served as a founding director of this QUP, which is an institute for quantum sensor development. And then I proposed some new quantum sensing methodologies for particle physics and cosmology with some theorists. And I also enjoy to work with theorists, including Fabio. Actually, we wrote some paper together, a bit of phenomenology. So that's my sort of background, and then I define myself as a particle physicist looking at the universe. And then why did I change my subject? Well, of course, several things, but one obvious thing is this, Planck satellite was a historic success, and then that was really, from particle physicist point of view, was really a great project for fundamental physics as well. Of course, Planck gave a lot of legacies for astronomy as well. But then this is my first visit to Bologna, and then Bologna people here are really made a great contribution to Planck, obviously, needless to say. So another version of my self-introduction is something like this, because a lot of particle physicists were fascinated by, this CMB projects. And then I just put, my faces for all the, but basically there's a lot of particle physicists now, jump into cosmology. Yeah, you may take the photo if you like. Okay, so now since I said I'm a particle physicist, so this is sort of my version of the introduction of standard model particle physics, which are based on really few principles which are hard to reject. I mean, it's really fundamental. These are really fundamental. And then I don't need to go into each detail, but the point is, it's really, really successful. And then for each item, each principle, each was worth for a Nobel Prize, as you know. And then this describes nicely three basic types of interactions. So that's a great success of particle physics in the 20th century. And then, as you know, this particle physics now is based on these particles, elementary particles. And the one obvious thing you notice is that if you look at this diagram, you see lots of spin 1/2 particles and spin 1 particles for gauge interactions. There's only one spin 0 particle, which is Higgs, discovered about 15 years ago. And then, so spin 0 is special in the standard model. That's obvious feature. And then let me turn to then cosmology. Now, thanks to Planck and other measurements, we do have concordance model of cosmology, Lambda-CDM. And in a nutshell, that's based on the general relativity and the cosmological principle. And with high symmetry, it's really turning to very simple this expansion equation, Friedmann equation. And then with initial adiabatic Gaussian perturbation, you can really beautifully describe the measurements. And then this from Planck. And then so these are just described by 6 fundamental parameters. And then of course, you need to introduce dark energy, dark matter, in addition to known particles. So that's a very nice sort of a triumph. Now, but the thing is, if you try to combine these two, I must say there are 5 mysteries. This is, since I'm a particle physicist, this is sort of a particle physics point of view. There are 5 mysteries unresolved. And then the first one is the cosmic inflation. You need the accelerating expansion. And then no particles, known particles can create this acceleration of the space, just the deceleration. So it's the particle physics or standard model we know is like a car without any, accelerating, pedal. So that's a big problem. And the baryon asymmetry is not explained within the standard model. And the neutrino properties are, of course, we know neutrinos, but there's little known mass, Dirac versus Majorana, and the number of neutrino species. I mean, sterile maybe. So there are many unknown, unresolved questions. And obviously dark matter and dark energy. So these 5 mysteries cannot be explained within the standard model of particle physics. So, and then if you think about the resolution, a resolution of any of the 5 mysteries will revolutionize our picture of the universe. And in many cases, resolutions, meaning beyond the standard model of particle physics, require new spin zero quantum fields, which I'm gonna show you in a minute in the next page. And then since in spite of all the effort so far, we haven't really found new spin zero quantum fields or particles yet. So that means, that indicates we need new eyes for this to discover some new spin zero quantum field for some breakthrough. As I told you already, there's just one spin zero particle in the standard model, Higgs. But if you look at all the proposals beyond the standard models, you see for example, inflaton for inflation, dark matter candidates, QCD axions, and axion-like particles, superstring-inspired particles such as dilitons, and superpartners in supersymmetry, etc. All above, all shown here, are spin zero scalar or pseudo-scalar particles. So this is the situation today. So I'm trying to give you some big picture I have. So we need to pursue this new world of spin zero. So that's really, really the key today. And then coming to this cosmic inflation, now, today my talk, since as Fabio introduced, I'm the founder of this LiteBIRD project. So people usually expect me to just talk about LiteBIRD sales talk. But today my talk is sort of a bit different. I'm trying to give you some big picture and then try to give you some the CMB polarization projects. I mean, what community is doing. So then coming to this physics of cosmic inflation, the leading hypothesis is to introduce this new spin zero or scalar field called inflaton with potential as a source of acceleration. And this really looks like this Higgs potential. And in case of single field slow roll inflation, without giving details, this is sort of the simplest model we can think of for inflaton. So we do have 2 important relations. One is this potential should be given like this, where I introduce a very important parameter today called the tensor to scalar ratio, R. This is a key parameter. And then if this key parameter is, say, like 0.01, actually this potential of this inflaton should be close to the ground unification theory scale. Out of nowhere, this is really intriguing to me, actually. This ground unification is a proposal, a theoretical proposal to unify 3 fundamental forces. And then that, if you introduce supersymmetry, for instance, you naturally get this 10 to 16 GeV. But out of nowhere here, we are also discussing this ground unification scale, GUT scale. It's just a sort of a intriguing coincidence, I should say. And then the second one, this is tensor to scalar ratio. in case of the simple model, you can have this sort of a rough description where this delta phi introduces a characteristic scale of inflaton field in which the inflaton potential changes significantly during the inflation. So this is a sort of some energy scale this model has. And then this is divided by the Planck scale, Planck mass. And N is this E-fold, the number of this inflation, this E-fold. So with these two numbers, you can sort of predict the value of R. So these two relations are really, really important. And then with this, we do believe that the measurements of this tensor to scalar ratio to the level of 0.001 or so would provide a fairly definitive statement about the validity of the most important class of inflationary models. There are always ways to create some models with a smaller tensor to scalar ratio, but at least one class of model, this 0.01 is really the milestone for the, this is sort of an experimental target. So how do we measure this? And then, so here, this cosmic microwave background comes in. So the testing cosmic inflation and quantum gravity with polarization of cosmic microwave background, or CMB. So what is predicted here is that during the inflation, the gravitational waves should have been created because of this rapid expansion, accelerating expansion of the universe, and that remain in the universe. And then when the cosmic microwave background was emitted, it should have affected the cosmic microwave background, namely the in the pattern of the polarization sky, namely this so-called the CMB B mode curve pattern of the CMB polarization map should have been created as a sort of a fingerprint of inflation. And then we do know that by far this is the most sensitive probe of the primordial gravitational waves predicted by inflation. So this is what we are chasing with the CMB polarization. So here's the CMB power spectra today, the temperature, and then this is EE and BB. So let me explain what these are for polarization. So if you think about the polarization map, you can, of course, there are two sort of degrees of freedom. If you just look at one point in the sky, so you can define the intensity of the polarization and the direction, the two parameters. But if you look at the polarization field, another possible definition is that this parity even divergence and parity odd curl. So this divergence part is called E mode, and the curl part is called the B mode. So by decomposing this this polarization pattern into this E mode and B mode, you can like just this intensity T temperature mode, you can make a power spectra of this polarization E mode and B mode, and then thanks to Planck and other ground-based projects, you have a beautiful this temperature power spectrum. And now this E mode polarization even parity even pattern is also measured fairly precisely. And then whereas this the B mode is really we are just starting measuring that. But so we do see measurements here. But these are not the primordial inflationary V modes. This prediction of inflationary V mode is shown here for the case of R equals to 0.01. And what are these points? These are the V mode due to lensing, gravitational lensing. What does that mean? So suppose there's just an E mode on the sky. So if you have this lensing, the light could be bent, and then as a result, this pure E mode sky could create some V mode. And then that's a lensing V mode. And then that's been observed by several projects shown here. And then, but this is secondary and not the main target we are chasing. Although this lensing B mode also gives you a lot of useful pieces of information for cosmology. So this is a current situation. And then what you want to do, this is from LiteBIRD slide. So let me just explain, use this. So you have measurement of the polarization sky using polarization sensitive detectors. And then with some proper foreground removal, you extract this B mode map. And then once you get the B mode map, you can just make a spectrum by doing the spectral analysis, just like what you did for Planck for the temperature. And then, so the one important thing is that the primordial B mode power is proportional to the tensor to scalar ratio R. So the intensity or the amount shown here. So this is a prediction of the primordial B mode for R equals to 0.01, I think. Yeah, and then this, if this is a say R is 0.03, then you should have larger this power shown here. And then currently there's a limit from by combining this ground-based project BICEP2 keck and Planck, and then the current limit at 95% confidence level is R equals to 0.03 or so. And then what we want to really achieve is to go down to 0.001 or so. So we still need to go, factor 30 or so. And then, so that's why we are proposing this LiteBIRD. But, if you really succeed to discover this, it has a huge impact because this is going to be the direct evidence for inflation. And this gives knowledge on the inflation energy scale. And arguably, this is going to be the first evidence for quantum fluctuation of space-time. It's really huge. And then that will give you insight on quantum gravity, including string theory. So because of that, if you look at, for example, this final report of the task force on cosmic microwave background, it's like about now 20 years old, but still, this statement is valid. Detecting primordial gravitational waves would be one of the most significant scientific discoveries of all time. So that's why we are chasing this primordial inflationary B mode of CMB polarization. But that's not only LiteBIRD, since we just have this limit around 0.03, and then the true value could be around 0.03. So there are lots of activities ongoing on ground, and the balloon is space proposal. So there are lots of ambitious projects with different technologies, different systematics, and I don't have time to explain each of them, but let me just introduce the projects I've been involved in, which is this polar bear and Simon's Observatory and CMBS4 before coming to LiteBIRD. Just very briefly to give you the scene we have right now. So polar bear is a dedicated was a dedicated CMB polarization experiment located at 50 to 100 meters in Atacama Desert in Chile. And then we got first light January 2012, and it was expanded to the Simon's array from 2018. And then since technology-wise, this is really the trend recently. Many experiments, CMB experiments, are using this transition edge sensor superconducting detector array. And then in case of polar bear, we had this 35 arc minute beam for 150 gigahertz. So this the aperture, the primary is effectively 2.5 meters. And then so here is a picture of our TS array developed at the UC Berkeley. So we have 1,274 TS bolometers on this array. So it's a really powerful instrument. And then we had many important cosmological publications, including first evidence for B-mode polarization lensing based on purely CMB information, and constraints on cosmic birefringence and primordial magnetic fields, primordial B-mode search, getting the best result in Chile, and then the cross-correlation cosmology results, and precise measurement of the Hubble parameter with E-mode observations. This is the E-mode we obtained from polar bear. As you know, we have this so-called Hubble tension today. The late universe measurements differ from the early universe measurements coming from CMB by something like 4.5 sigma. And, that's still an open question. And this polar bear has been contributing to that to some extent. Now, but let me today stop by a little bit different topic from polar bear. This is probably amusing, and then not many people know about that, so that's why I picked that. This is a paper last year we published from polar bear, and this is a search for ultralight actions at polar bear. Just spending 5 pages. The polar bear collaboration. The multiple institutions from 7 countries, I think, supported by various agencies. And so what I'm talking about is like this. So ultralight action or light particles or ALPS. As I told you, polar bear main task was CMB observation and then the polarization. And as a calibration tool, we observe the Crab Nebula or Tau A periodically, if possible, every day, basically. And then Crab Nebula is a polarized astronomical source, very nice one at millimeter wavelengths. And then, this Hubble HST, beautiful image. But if you look at Tau A, at polar bear, it looks like this. So it's not a point like, even with polar bear, 3.5 arc minute beam, you see the structure like this. So one thing pointed out was the following. If there's a really, really light, very light axion field, it's basically the mass is almost nothing. So then if so, it really looks like photons in a sense. I mean, what I mean by that is that it behaves as a classical field with large number density. And then what could happen is that the it it fills the universe, and then so this the light emitted from tau A and reaches us, and then polar bear measures that, and then locally this action field serves as almost sort of a birefringent material, and then but because of finite mass, it gives us really a very slow sort of a oscillation of this birefringence. So if we do have that sort of a very light axion field, we expect to observe very slow sort of a change of the polarization angle of tau A. So we made that measurement, and then we scanned all the possible frequencies we could, touch on. And then here's the result. And then at some special frequency, you have this 2.5 sigma excess oscillation-like structure. And note that since we had a scan, this 2.5 sigma is including so-called Lucas-Ware effect. So this is a global significance. If you just pick that frequency and then check the significance, you get something like 4.4 sigmas. But you need to stick with this global significance. And then this, if you interpret this as an axion field effect, and then that corresponds to really light, like 10 to minus 8 times 10 to minus 22 electron volt. Of course, this is just 2.5 sigma. So if you put the limit here, still this gives one of the world's best limits for this very light axion mass range. So we published this result, Physical Review D, last year. Now, since I'm an experienced particle physicist, I experienced several, like 3 sigma anomaly, even 4 sigma anomaly. So this is interesting, but we need some sort of a calm discussion. So we went through possibilities, and then, well, of course, first one is statistical uncertainties. Of course, this could explain the result. So we need more data. And then now you ask yourself the residual systematic errors. We went through the possible systematics, and then it was really a thorough study. So we think it's unlikely this is due to systematic uncertainties, though this, I mean, you never exclude that possibility completely. And yeah, you can ask, is this due to some intrinsic variability of tau A? Well, it's single mode oscillation is unlikely for this broad, several light year wide Crab nebula. And Crab pulsar is at the center, but the intensity from that should be much, much weaker. So, and then there's no intrinsic variability report from any other measurements. So it's also unlikely. And then I need to point out that this is not actually consistent with bound from the X-ray spectrum of the quasar. So obviously, if this is real, to be real, this should be reconciled with that measurement. So the best is to get more data. And luckily, we do have more data in the can already, because polar bear was, as I told you, upgraded to Simon's array. And then this is one of the receivers we developed at KK with the this focal plane, more powerful focal plane developed by UC Berkeley. So we do have data, and then we are analyzing data right now. So hopefully we can confirm or deny that hint we observed. Okay, so that was the detour. Now, I talked about Simon's array, but now now more powerful Simon's observatory is online. And then its target sensitivity is sigma r of 0.003. So the order of magnitude improvement is the goal of Simon's observatory. And these are the photos I took because I was in Chile last December. So these are photos last December. So the Simon's Observatory has 3 small aperture telescopes, SATs, and 1 large aperture telescope, LAT. And then SATs are already have already started taking data. And as usual, at the beginning of experiments, you are struggling with characterization and some issues here and there. But this is becoming really strong. And then so we do hope to get some first results publication in a year or 2 time scale. And then this large aperture telescope LAT is the commissioning is in progress. This is really a huge, cryostat. You see the person here. It's really impressive, huge one, and this 6-meter main dish. And then so this commissioning this year should be ongoing. So you will hear more and more results in coming years from Simon's Observatory. And then it's a big collaboration from many institutions. And so as shown here, this is Simon's Observatory. And even more ambitious ground-based project is CMB stage 4 or S4. And then this is a slide from Jim Strait given last December. This is a US-led effort beyond Simon's Observatory. And so CMB-S4 aims to be the definitive ground-based CMB experiment. And so it has some history. And then it got, for example, at evaluation at DOE, it really got highest rank for the future project, even in particle physics from particle physics community. So and then so this is of course taking time for preparation. So it should be online in 2030s. But until then, the CMB, Simon's Observatory is gonna, continue taking data and lots of data actually, and then CMB-S4 hopefully will be online, and then as you might heard. Before that, so here is the one-page summary of the CMB-S4 primary science goals. So as for this tensor to scalar ratio, it's will cross a critical threshold, which I said the 0.01. So this statistical uncertainty goal will be 0.005 at the CMB-S4 to discover or rule out the natural models of inflation. And it also has a nice list of science goals on the relic particles and matter mapping and the time domain science. So it's really going to be a gorgeous project. And then recently, one obstacle is that the NSF decided not to offer the South Pole for CMB-S4. So now CMB-S4 is working on a new strategy for observations only from Chile. So it's going to be a bigger upgraded version of Simon's Observatory. So so that's what the CMBS4 science collaboration has been working on right now. And obviously, in addition to the reformation of the hardware design, which should be, in a sense, similar to Simon's Observatory. So it's natural to think about the collaboration with the Simon's Observatory. And also, in addition, they're gonna keen on combining results with the South Pole activities and also LiteBIRD. So this is again a slide from Jim Strait. So from the CMBS4. So they are thinking about that sort of synergy. And so that will reduce the total data required to be taken by CMBS4. So we do believe that the best scenario will be to have, I mean, from the CMB community, to have the very powerful ground-based project plus relatively small CMB satellite. So that powerful combination will be the way to go. And then, so this CMB S4 strategy is consistent with that statement. Now, let me turn to LiteBIRD. So this is a standard LiteBIRD, the logo and participating institutions. So LiteBIRD Joint Study Group has over 400 researchers from Japan, North America, and Europe. 5? Okay. Okay. Yeah, so actually more than half are from Europe. So very powerful European participation. And then here's an overview. This is JAXA's L-class mission. And then it's going to have all-sky 3-year survey and from Sun-Earth Lagrangian point L2. And then it's going to cover a large frequency range from 40 to 400 gigahertz with 15 bands with TS array. So the corresponding beam size will be between 70 to 18 arc-minute. And then so the final combined sensitivity will be much, much better than all the CMB projects achieved so far. So that's around 2 microkelvin arc-minute. So that's the target or goal. So actually, a bit like CMBS4, LiteBIRD also now doing a reformation studies after the JAXA mission definition review. Now LiteBIRD is under the rescope studies to consolidate the mission's feasibility with the same scientific objectives, which I'm going to explain in a minute. So then we are already in this reformation phase that will continue until late 2025. And then hopefully we'll enter phase A and phase B after that reformation phase. Just LiteBIRD observations is going to be rather different from what Planck did. So this is like a spinning top with this configuration. And the idea is to have the smallest possible systematic uncertainties for the polarization measurement. So the scope or target is much, target is different from what Planck had. So because of that, this scan strategy is rather also different. And otherwise, having TS parameters just like a polar bear, Simon's array, Simon's observatory, and then doing the foreground removal, extracting B mode, and then have the spectral analysis. That part remains the same. And then, of course, the challenge lies in the foreground removal and control of instrument systematics. And so these are really the challenges we are facing. And then already at this stage, we have been doing really high-level end-to-end simulations. And then so far, the results are so far so good. And there's, at least for now, there's no showstopper. We say we can achieve the target of this at 1 times 10 to minus 3. And then if you compare our this R value contour with the Simon's observatory, you see this nice improvements. And then this is for the model, one of the most likely models called the Starobinsky model, which has a firm prediction about the value of R and with the smallest number of parameters. And then there's a huge impact for fundamental physics. Just give you some example here. This, I just talked about this inflaton, and then there's a model called the Higgs inflation, which means that basically Higgs behaves as an inflaton in high energy, and then that also gives you basically pretty much the same prediction as the Starobinsky model, and we hope to really test these models. And let me just skip this because of the time. And so that's just one example. And but having said that, I should really emphasize LiteBIRD has really rich science outcomes as listed here. We can observe very nicely EMOs also, and that will be really good for reionization science and giving some impact on the neutrino mass. And and also we can use LiteBIRD measurements for cosmic pipe refringence measurement and Snell's Levitz effect studies, primordial magnetic field search, and elucidating anomalies, Planck indicated, for instance, and also galactic science. And since I'm running out of time, I guess just show you some example. Because of the very nice, powerful instrument, E-mode power can be measured to the limit of cosmic variance, which gives you factor 3 improvement from Planck, and that gives you some insight on the reionization history. And then that also can be used, this, better measurement of the optical depths can be used to mitigate the degeneracy of the parameter, this optical depth and some of the neutrino masses. So because of that, by using this LiteBIRD result with other measurements, combining with everything, you can hope to come down to really impressive precision of the neutrino, some of the neutrino masses. So the 5 sigma detection of the minimum mass for normal hierarchy could even be possible. So, and then you can also, thanks to this 15-band measurements, you can also address the spectral distortion, and you can measure the Y factor nicely. And compared with Planck, you can come down to really low, like a multiple of L of 20, and that gives you really the legacy information about the hot gas distribution of the universe. So that will be can be used for many purposes in astrophysics. And another thing I want to emphasize is that full sky maps in 15 millimeter wave bands will offer rich new data sets, which enable exciting breakthroughs in astrophysics and astronomy. Actually, although LiteBIRD dish size is smaller than Planck dish, because of the much deeper measurements, much better measurements, you don't have to compromise the angular resolution. So actually, for the high galactic latitude, you can have the actually better angular resolution than Planck. That's the expectation. Then you can really, this is an example comparison of the this polarization sky. So you can really study many things about the our galaxy. So that's probably a very important message I should give you. And then, so I'm coming to the conclusion. For LiteBIRD, take-home messages are following. The primary scientific objective is to search for the signal from cosmic inflation, either making a discovery or ruling out well-motivated inflationary models. And the measurements of LiteBIRD will also provide us with insight into the quantum nature of gravity. And it also has rich astrophysics, astronomy outcomes. That's about LiteBIRD. And then the summary of this entire talk. So there are many new physics models, and then that introduce spin zero particles. So that's where we live now today. So since we have not found such spin zero fields yet, we shall invent new eyes to make an experimental observational breakthrough. And here, I just introduced new measurements, ideas, examples. For CMB polarization, the Simons Observatory CMB is for LiteBIRD. And I just picked this ALPS search at Polar Bear. So it's really important for us to chase whatever spin zero particles propose. So the last sentence here is that at the beginning I tried to put some specific numbers here, but instead I just share this statement. I expect to see X, that's the name of the spin zero particle, as a manifestation of the new world of spin zero in Y years. So please fill X and Y by yourself to test your optimism. Thank you very much.
Thanks, Masashi, for this inspiring talk and this survey of CMB polarization experiment. Any question? Stefan.
Thanks. A couple of questions. One is about LiteBIRD, and if you can tell us which is the status of an observatory and when is expected to launch.
Yeah. Current target is launch in Japanese fiscal year 2032. And that might be shifted depending on the outcome of our reformation studies. So because of this reformation studies, actually both for LiteBIRD and CMBS4, I couldn't go into the instrument design much. But this is our baseline until last year. And then we are now discussing how to simplify our telescope design. It could be just one telescope without sacrificing our sensitivity much. So that's sort of we are working on some trade-off studies until around the end of this year. So that's current status.
Another question is about the foreground contamination.
Yeah.
What are the most critical ones, and is the setup already defined how to solve any contamination and all the systematics affecting this?
Yeah. So obviously for the low frequency, the synchrotron radiation, and then the high frequency, the dust polarization, and dust emission. these are the two biggest enemies. And then thanks to this 15 bands we plan to have LiteBIRD, we can use this different frequency dependencies. And then, so this program cleaning business is really a big industry. There are several competing methods. And then, as I just give you the summary in my slide, just one sentence. We satisfy this target after the foreground cleaning, but this is really still ongoing study. And then this is just a snapshot probably last year, how we model the foregrounds and then how we, remove and then how many parameters, like more than 6,000 parameters to remove, clean the foreground and stuff like that. This is still ongoing. Yeah.
So maybe I can also comment that concerning the fact that LiteBIRD is in space and observing 15 frequencies, this number of frequency is much larger than any other ground experiments planned. And also the position in space is quite important, avoiding atmospheric contamination.
Yeah, curiosity. So when you mention quantum gravity, the possibility for training, do you mean you already have some direct unique predictions from quantum gravity theory that are collected and differentiate between them, or just?
It depends on how you define it, direct prediction. Certainly, we don't know the true quantum gravity theory. So, but whatever happens, if you in a small perturbation regime, what you introduce here is sort of a quantum mechanical commutation relation to the metric. And then since the Einstein equation is a sort of a field, the wave equation, you just plug the commutation relation. And then you have this firm prediction. This is already one big step forward toward the quantum gravity. So that's, in that sense, if we really observe this CMB B mode, primordial B mode, that will be a huge step. And beyond that, there are some, of course, theoretical speculation, but I just skip that because that's probably too early to say anything conclusive. For example, this is a recent example. This string theorists argue that there is a swampland. And then if we do observe this B mode with certain, if the B mode is fairly big, it should be in the swampland. So that has some impact on the model building based on string theory. That sort of thing can be what we can tell. And that is already exciting to me.
So I have a curiosity. If you go back to the constraint that you showed for the Starobinsky model.
Yeah.
So it's very fantastic prediction. So in particular for the tensor to scale ratio. But I am a little surprised by the fact that there is a degradation of the constraint for the T, for the spectral index. So I would expect to see an improvement for all the possible parameters when you constrain using this data. While in this case, there is a sort of degradation for the spectral index.
Oh, okay. It's not exactly degradation. For this LiteBIRD contour, we just take Planck result. Whereas for Simon's observatory, because of the better E-mode measurements up to high L range, you can add that to temperature measurements so that you can reduce the uncertainty on this scalar index.
Combination of the
Yes,
negative
yeah.
and-
So if we also take the Simons observatory measurement at LiteBIRD, of course, we can.
I can add this,
Maybe,
so I
maybe
did it.
Daniela thinks this week.
Oh, yeah. Daniela, here's the, one of the world experts, so.
So basically what you have is that LiteBIRD has a lower resolution, so you see less peaks. So if you take LiteBIRD alone and not
Okay.
combined with Planck or ground base, you slightly have a lower grip on the NS. Instead, Simons Observatory, as Masashi was saying, you can use also the polarization up to 5,000, and therefore you have a lot of grip on NS.
Yeah.
If you put
Okay.
together LiteBIRD and Planck,
Oh,
you
yeah.
supplement it, you have also.
Okay, no,
Yeah,
no,
so it comes from the different angular resolutions. Yeah.
Thank you.
Any other question? We are hitting the 12:30, so if not, let's thank Masashi. In the CNR meeting.